This session is on thermal energy systems, and my name is Ravi Prasher. I am one of the program directors at ARPA-E, currently running 2 programs on thermal energy systems. A little bit about me. I came from Intel Corporation. I was there in the R&D group for almost 11 years. I was actually the manager, the R&D manager for their electronics cooling group, and then year and a half ago, almost 2 years ago, I came to ARPA-E to look into technology development for energy systems related to thermal energy. And with me are my colleagues, Dr. Ilan Gore. He's a material scientist by background. Before coming to ARPA-E, he was with a startup looking into electrochemical batteries. And currently, he is the senior advisor for commercialization in the ARPA-E commercialization team. And my other colleague is Dr. Sawyer. You might have seen her in the other session on carbon capture. Her background is in chemistry, and she is an assistant program director with ARPA-E. And these 2 people played a very significant role while I was crafting my second program on thermal energy storage, because I really wanted to tap into their background on electrical storage and material scientists from Ilan, and really understand what are the new kind of chemistries that can be used to store thermal energy. And during the presentation, you will hear their perspective on thermal energy systems and what they have learned and what do they think, what their thoughts are on some of the new learnings that can be brought into this field. Okay, so with that, let's get started. So this session is, the purpose, in our opinion, for this session is to show you what ARPA-E is currently doing on thermal energy systems, and also to sort of give you an idea of why we are doing certain things certain ways in related to thermal energy. And finally, I would really like to use this session as sort of a mutual brainstorming between you and us on what are other possible game-changing ideas out there which in the future ARPA-E should potentially be funding in thermal energy systems. Okay, so why thermal energy is very important? I think it is a question which is obvious to a lot of us. We waste more energy than we use. And 55 quarts of energy that we waste, almost all of it is in thermal form. So that's why this is a very simple statement. It shows that, okay, it is very, very important. Now the question is, what are the main reasons for this waste? So the way we look at the program, if we take a 30,000 feet view, there are three reasons why we have such enormous waste and why we use less energy than why we consume less energy than we waste. One of them is there is absolutely more or less no integration between supply and demand. So you have a power plant at one place which is converting heat into electricity, and the second law, because of second law, you'll have some waste on the cold side, and that quality of heat is very, very low. And there's either you cannot convert it further into power, or you cannot really transport it to a long distance to use that for heating. And if you had a futuristic scenario, if there was a significant integration between where you're using the energy and where you are converting it, then you can potentially think of a system where you have multiple different kind of technology which will be needed. One of them happens to be thermal storage, because the supply and the demand, the way we consume and when we generate, they don't always match the timing. Of course, you will need other devices such as electrical storage and better transmission lines and whatnot, but today we'll just focus on the thermal energy in this particular session. So that is one of the main reasons that you have significant waste of energy. Second one is, which is again pretty obvious to this community here, is inefficient power conversion. I'm just showing an example of a power conversion in an automobile, and what you will see is that out of the total primary energy available in the fuel, only 25% of energy is used finally in driving a car. And actually even here, we are wasting, more energy is going in the exhaust, the tailpipe, than we are using to drive the car. So the question is that can we do something about it? There's significant potential here to harvest this waste energy. And we have a couple of very small projects on this, but we have not yet come up with a program dedicated to harvesting waste energy. And that probably could be one of the things that we can discuss towards the end of this presentation, that why we haven't done that yet. But again, the point is that if you can convert significant amount of this waste heat either into electricity or you use it directly as for heating purposes, that again will lead to a significant reduction in the amount of primary energy that we use. And finally, very, very important is the end use efficiency itself. So if you focus on the building sector, for example, then building sector consumes approximately 40% of our primary energy. And in the building sector, approximately roughly 50% just goes in heating and cooling. So we are talking about roughly 20% of our primary energy is just going in heating and cooling. But if you look at the basic technology of heat pump, that technology has not changed significantly in the last 80 years since Carrier invented air conditioner. And what I'm showing you here is that how far we are off today from the theoretical limit for air conditioning. We did these calculations for a given set of conditions, and what you see is that we are approximately 10 times away from the theoretical limit. So what is theoretically possible and where the efficiency is today, we are approximately 10 times away. And there are two reasons for it. One is, if you'll notice that it is with respect to the primary energy. That means it also includes the inefficiency of power conversion, and then using that power to drive an air conditioner or a heat pump. So there's an inefficiency associated with that conversion itself. And that's why if we look at this as a significant opportunity. And I'll talk about a program that I've been running for almost a year and a half or to tackle some of these, tap into this opportunity. Okay, I think I'm not going to spend too much time on this because if you attended the morning session, our Deputy Director of Technology, Eric Toon, he touched upon what makes an ARPA-E project. It is very important. I think it's very helpful for you as a potential applicant, that what are the things that we look for. First thing, without even worrying about the science and technology, we really look for that, okay, if it works, will it have a big impact or not? That's the most important question that we ask. The next one is it a transformative idea? And this is sort of related to what Arun was talking in the morning about a new learning curve. Then we also look at bridging new scientific discoveries or scientific discoveries in multiple fields combined together to make a new technology. And finally, team is very important. Finally, you can have a great idea, but if you do not have a great team to deliver it, then that idea never materializes into a great technology. So these are the 4 attributes that we look for in any ARPA-E proposal. Okay, so now let me jump straight into what are the programs that we have and why we have chosen to run those programs. Currently we have 2 programs. One is, the short form of a program is called HEATS. That's a relatively new program, started approximately a month ago. The HEATS, the full form stands for High Energy Advanced Thermal Storage. So that is the program on thermal storage. And the first program which I started at ARPA-E is on building energy efficiency. The full form of BEAT program is Building Energy Efficiency through Innovative Thermal Devices, where we are primarily focusing on heat pumps. How to make heat pumps significantly much efficient than what it is today. And I showed you the earlier graph where we are approximately 10 times away from the theoretical limit. The target in that program is to cut that difference between the theoretical limit and what is the performance today by approximately 50%. Okay, so let me touch upon a little bit on the BEAT program and give you some examples of different pathways that different teams are looking into to make a significant jump in the performance. And when we wrote this FOA, when we released this FOA, we were not looking for sort of improvements in one component of a complex air conditioning system. We were just looking at, excuse me, can you come up with a totally different pathway to do air conditioning? For example, this chart is very familiar to at least anybody who has done undergraduate thermodynamics in the mechanical engineering community. This chart is called a psychometric chart. And what it shows you is a map of temperature and humidity, right? So air conditioner is used not only to cool and make the air cooler. it is also used to make the air drier, to control the humidity in the air. And how is it done today? So for example, if you are at that red dot, some high temperature and high humidity, and you want to come to this blue dot, which is low temperature and low humidity for whatever is needed to make us comfortable inside a building, the way it is done today, and which hasn't really changed in last 80 years, is that what you do is that you basically make the air so cold that the moisture just condenses out of the air, and you see water droplets coming out. If you look at your air conditioner on the condenser side, there you'll see a lot of water puddle. So you make the air very, very cold, and sometimes the air is so cold that you might even have to reheat it. So again, so first of all, there are two energy inefficiencies right here. One is you spend a lot of energy in making it unnecessarily too cold, and then energy in heating it back to comfortable temperature. So the question that we asked in the FOA was that, can we do this? Can we just go vertically down, and so isothermal dehumidification, and decouple the dehumidification completely from cooling? Now you have only dry air going into the chiller. And can we do it in a very cost-effective manner? So just to give you an idea how one of the teams are looking into this problem is, so they are looking into a membrane which is very selective to water molecules. So imagine, say, you have a membrane and moist air is going next to the membrane, and you can pull out, this membrane will just pull out the water molecules, suck the water molecules out of this moist air, and leave the oxygen and the nitrogen behind. And that way, only very, very dry air without the moisture is going to the chiller. That can significantly boost the efficiency of this kind of a system. And I think based on some of the early results, it looks like that it can even beat the 4 target that we put. That was one example. We were actually in the beat it, we funded approximately 15 different projects. We were looking at, we had a portfolio of different technologies that we funded. One of them, another example that I'm showing you here just to give you an idea the kind of project that we funded, is on thermally activated air conditioners. So the idea is that, okay, most of the air conditioners, they use electricity, which is your vapor compression system. So you have electricity is the energy input, then you get hot and cold. There is significant interest in using thermal energy as the energy input and then getting hot and cold. And that is known as absorption chiller or an adsorption chiller, right? But if you look at the market share of these systems, it's very tiny compared to vapor compression systems. And there are multiple reasons for that. One of them is that these systems tend to be very, very bulky, and economies of scale only work if you are looking at a much larger chiller. So the challenge was that, okay, can you reduce and shrink the size of these systems by 2 to 3x, or even more? And that has other advantages, apart from the fact that you can make it much more modular and you can start potentially using these systems at a smaller scale. When you look at the cost of an air conditioning or a heat pump, half of the cost is typically in the technology and half of the cost is in transportation and installation, which sort of scales with the weight of the system. So this, if you can achieve this with a higher efficiency, it can have a significant impact on the cost of the technology all the way from manufacturing to installation. So just to give you an idea, one of the teams that we funded is looking into this new material called metal organic frameworks. These materials have been investigated for last decade or so for storing hydrogen or storing natural gas. But this team figured out that they can use this material to store refrigerants. The state of the art is silica gel, which basically works only with water as a refrigerant. But this material can potentially work with water and a lot of other refrigerants as well, and can absorb 2 to 3 times the weight and the volume of what silica gel can absorb. So that is where the breakthrough can come in. The new material used for delivering a new types of absorption chiller. With this, I'm going to change gears now. I'll talk about the HEATS program, the thermal storage program. That is a relatively new program, as I said, and it's very, very important that we realize was one of the biggest white spaces in the energy sector. And for that, what I'm going to do is I'll ask my colleague Ilan to talk a little bit about his experience on electrical batteries, because at least from outside, being a thermal scientist, I realized that electrical battery community has done a significantly better job in advertising their technology and what are the potential uses of the technologies are compared to thermal energy technology. And maybe I think you guys would love to hear from a person who has worked in the electrical battery sector and he's working now on the thermal storage.
Sure. Is this on? Can you guys hear me? I'm not sure it's on, but hopefully you can hear me. So my background, as Ravi mentioned, was in electrical storage. And one of the things that really excited us about this program, Ravi was already thinking when I came into ARPA-E about thermal storage. And what attracted the agency to thermal storage as an area to explore was what's written here as white space, right? So what does that mean? ARPA-E generally wants to do things that aren't already being done, whether that means new technology approaches or new opportunities for impact that others may not be looking at as strongly as they could be. And here, what we noticed was ARPA-E had two existing programs in energy storage, both really not just focused on electrical, but electrical and mechanical, but storing electricity was the focus of both of those programs. And meanwhile, 90 or so percent, if you look at the Sankey diagram, right, 90 or so percent of all energy ends up thermal at some point. And so the question was, well, where is thermal storage? Why don't we see anything? And it's not a matter that no one's been working on thermal storage, right? Hopefully there are folks in this room who have built their careers working on thermal storage. There's certainly been a lot of amazing work done. But the question was more, well, you pick up the recent issue of Science or Nature or Technology Review, and or the New York Times, and you have story after story about electrical batteries, and you don't see much about thermal storage, right? At least not until very recently, I'd say. Or another example is, you can talk to a head of R&D at a large company or a venture capitalist and ask them, what's the state-of-the-art battery energy density for vehicles? And they'll say 200 watt-hours per kilogram at a cell level. And you'll say, well, what's the state-of-the-art energy density in thermal storage? My guess is they wouldn't know. So this was a question of, okay, why isn't there a bigger community thinking about this issue, which is obviously important. So that was one white space, was about the community and about the interest. And I think the other was about the impact. Okay, so we have storage going into electric vehicles now, electrical storage. We have storage going onto the grid. We don't see that many examples of thermal storage being used in a widespread way today. And so why not? And that was what really excited us about this program. And I think Ravi will walk through a little bit on how we tailored this program to really focus on what are the potential impact areas in energy that we could use thermal storage for, that either shed light on new impact areas that people haven't been thinking about as much as maybe they could, or that give an opportunity to take really new technology developments that have happened, coupled to these new markets that are growing, and try and merge the two to create some new innovation.
One thing which I would like to ask you, coming from that community of electrical storage, that we have chatted about it, that are the systems, the inherent chemistries, is it more complex in electrical storage compared to what you have seen for thermal storage, and does it offer another benefit?
Yeah, so I think, obviously one of the big things that attracted us to thermal storage is if you look at electrochemical batteries, a lot of these systems, you're talking about complex systems, complex materials, and in many cases expensive systems and expensive materials, with applications like storage for the grid and even storage for vehicles, where cost is probably one of the biggest drivers for adoption of new technologies. So you sit here and you think about the fact that, thermal storage, even phase change of water and ice, can get you to the same order of magnitude of energy densities as a lithium-ion battery or a portable battery today, is pretty darn interesting, and given the fact of how much simpler those systems could be, is something that was pretty attractive.
Okay. All right, so let me actually talk a little bit in details about some of the areas that we have funded in the HEATS program. One of them, which is actually an example where you can say that, okay, thermal storage systems are already being commercially deployed, is in the area of CSP, concentrated solar power. But what we realize is that what I'm showing you is the efficiency of a solar thermal power plant as a function of temperature for different concentration ratio of sunlight. And what you see is there's a peak. And that peak is, there's nothing fancy about it. Either efficiency or power conversion increases with temperature. However, your heat losses also increase with temperature. So there are two competing effects, and which basically ends up being where the efficiency overall of the plant peaks with respect to temperature. Current systems, which is primarily parabolic troughs, they work at temperature around 400 degrees Celsius or so. And our own internal analysis, as well as some of you might be familiar with the Sunshot program at DOE, which is targeting to make solar cost competitive with fossil-based power, shows that unless, for the CSP part, unless you really go to higher temperatures, it will never become economical compared to if I compare it with fossil-based plants. That's when we realized that, okay, so you got to go to higher temperatures beyond 600, 700 degrees Celsius, and there is not a single reliable thermal storage system out there which can actually store heat at that temperature reliably for the next 20, 30 years. So that was a white space that we realized, and so one part of the HEATS program is looking into utility scale, where cost is very, very important, utility scale thermal storage for temperatures greater than around 700 degrees Celsius or higher, right? And that is the focus of one of the parts of the HEATS program. And actually, which is not shown here, is that you can use the same technology also to store electricity from the grid. Just imagine where you have a heat pump, and the heat pump is driven by the electricity from the grid, and it can use that electricity to split hot and cold. And when you need the electricity, you run that heat pump in an engine mode, and you can get the electricity back. So same technology can also enable electricity storage at the grid level. And there are some studies that we have seen, it shows that there are challenges, but if those challenges overcome, this can be very, very cost competitive and compete with pumped hydro. All right. So that was one example where we are looking at a very large scale, utility scale, where cost is very important, thermal storage system. Other end of the spectrum in the HEATS program is where we are looking at a very, very compact, very high energy density, modular, mobile thermal storage system. And the reason is that what we came across is a great opportunity in vehicles. So if you look at electric vehicles today, depending on where you're driving it, say you're driving it in Washington DC in this weather, or maybe a little bit colder than this, as much as 40% of the electrical battery power goes in providing climate conditioning. 40%. And the reason is that if you look at your IC engine vehicle, you are not paying any penalty for heating. The heating is free. That's actually one of the best examples of combined heat and power. Whereas in electrical batteries, electrical cars, you have a resistive heater. So you first of all use electricity to charge a battery which came from a thermal source, and then you are using that electricity to get heat again. So what we thought about is that, okay, what if you also have a comparable energy density thermal battery in the car, both hot and cold? Significant scientific and technological challenge. But if you can have that, that means while you're driving the car, you do not have to use the electrical battery at all for climate conditioning. And that can also be used for battery thermal management itself, because battery performance is very sensitive to temperature. Not only that, that is one example for the electrical battery, even for electrical vehicles. Even for IC engines, in a city driving condition, a cold start, which is at 25 degrees Celsius, if you start your engine at 25 degrees Celsius, then approximately 10% of the fuel is unburnt, which comes out of a tailpipe. So it has fuel efficiency issues, impact, as well as emissions impact. So imagine that you also have a thermal battery in an IC engine car. And so you always start the car in a from a hot starting condition. So that can have a significant impact both on efficiency, fuel efficiency, as well as emissions. But here the challenge is again, how do you get to a very, very high energy density system, thermal energy system? So we analyzed two modes of thermal energy storage, which is you'll find in multiple papers and books. Thermophysical storage, where either you are just heating up something and storing the heat sensibly, or a phase change, or you can store the heat in a chemical bond. And what you see is on this graph is that both of these systems have their own pluses and minuses. So thermal physical storage has very high volumetric energy density but very low gravimetric energy density, right? Whereas thermal chemical storage has very high gravimetric energy density but pretty low volumetric energy density. And thermochemical storage has one advantage is that you don't really need an insulation because you are storing that heat in a chemical bond. So the question that we posed is that how can we get there? Can we get best of both worlds? And that would actually, if you look at the question mark there, that is an energy density which is comparable or higher than lithium-ion battery. So that's when I was looking at this data, that's when I pulled Karma, who has a chemistry background, and we started brainstorming that what are the other ways, are there other avenues in chemistry community which can be used for significantly increasing the energy density. And I think I would like to hear from Karma that what are her thoughts and what are the things that she sort of learned during the formation of this program.
Can you guys hear me? I don't know if this is on, but you're good? Okay. Yeah, as Ravi said, I'm a chemist by training, and he pulled me in to work on this thermal storage deep dive about a year and a half ago, and I was completely new to the space. I've been working in the carbon capture community really since I was doing my postdoc. But this is a very convincing man here. He had me on board very quickly. And what I realized when I looked through this data, kind of with the view of a chemist, I saw a lot of similarities between all of the different reactions that are plotted up in the pink box here. One of the big ones is that you're not storing heat in covalent bonds for the most part. Another thing is that every reaction up there has at least one gaseous component. And it's really those type of large-scale similarities between these reactions that lead to the low volumetric energy density that you see. And my first instinct was to really dig in and say, are there technical ways around this? Are there new reactions that you can find? And I think we had some really interesting discussions internally about it, but probably the most important take-home that I had from doing this work was that, just like myself, the chemistry community is really unaware of this challenge. They don't even realize that the reactions that they know in some cases and they're familiar with and the materials that they're spending all their time in lab dealing with could have really incredible impact in the thermal sciences space. So really there's this need for a new community and this cross-disciplinary skill set to come together. We hosted a workshop a little over a year ago where we invited chemists and material scientists to come and speak to the thermal engineers and brainstorm around kind of how we could find synergies between the new materials that they're working on every day or that they're familiar with from maybe even their undergraduate level classes and the needs that people have in the thermal sciences community. And I think we got a lot of great feedback from that day. Probably one of the most important take-homes, though, was that the chances of us hitting kind of that gray space, that gray box up there, are highest when you couple some of these new innovative materials and reactions that haven't been used for thermal storage with a really smart and innovative system design. So yes, in the end, I think that we found a good space for synergies in the community, and I really hope that continues forward in the broader chemistry space.
Thanks, Karma. Karma pointed out that we had a workshop where we invited, chemists, material scientists, physicists, thermal engineers, mechanical engineers, to brainstorm. And after we have funded approximately 15 projects or so in this HEATS program. And what we realized was that almost around 40% in the teams, PIs and co-PIs, around 40% in the team are from the basic sciences, chemistry or material science or physics. And they have teamed up with, with mechanical engineers and thermal engineers to develop not only better material but also a very, very good system. And that actually will lead to this slide where we are talking about, okay, it's not only about the material. Finally, the cost and the performance depends on what the system delivers. This is one example for the solar case where you're storing that heat and converting it back into electricity. So there, it is very important to maintain the quality of the heat. And so the heat exchanger design and overall system design becomes very, very important. So we always kept that in mind, and the way we set up the 4 targets for different sections was was based on what is really relevant there. So the cost of, as you can see here, for the for the part of the FOA on solar energy generation, solar electricity generation, the FOA matrix were set based on exergy, were not based on just heat storage. Because that is very, very important to keep in mind, that engineering is as important as some of the radical ways of storing the thermal energy. Okay, so let me just give you a couple of examples of projects that we have funded on two of the different type of application areas that I talked about. One is on the solar side, where you're looking at a very large scale system. So the state-of-the-art material which is used is a molten salt. And the molten salts can, typically go up to 500 degrees Celsius or so. They're not cheap. They're very, very expensive. This particular team is looking into a low viscosity molten glass, which can go from 400 degrees Celsius to 1200 degrees Celsius. It can be potentially very, very cheap because your delta T has increased by 8 times compared to that of molten salt. And it will be low viscosity and will be made from earth abundant materials. So hopefully, if this is successful, this could be a paradigm shift. And the temperature they are shooting for, either you can run a supercritical CO2 cycle or a Brayton cycle, or whatever is the high temperature cycle that is available to you to get high efficiency. This is the example. Now let me give another example on the vehicle side, where as I said, energy density is very, very important. So this is a team that we have funded at UT Austin, where they're looking into sugar derivatives, and they're playing with the molecular structure of sugar derivatives to increase the heat of fusion by 2 to 3x. But energy density is only one aspect. It is also very, very important that how fast you can charge and discharge this thermal battery. So, excuse me. So thermal transport becomes very, very important. So they are looking into using this graphene foam composites to significantly boost the thermal transport of these materials, because typically these kind of organic materials have very low thermal conductivity. Okay, so these were the two sort of examples that I talked from the heats, which are sort of obvious that, okay, you're just storing thermal energy and using it later. During the program, while we were sort of brainstorming, we also realized that, okay, you know what? We can also use that heat to store the heat in the form of a fuel. And that, again, that realization came while working on the program and brainstorming about it. And also, I learned a lot about biofuels myself when I came to ARPA-E. I did not know much about biofuels. What is the basic physics behind biofuels? So what we found out that if you look at biofuels, from sunlight to energy stored in a chemical bond, it is approximately 1%, right? And whereas I'll talk about it, the target that we have for the HEATS program is to have sunlight to fuel efficiency greater than 10%, actual practical efficiency. And the reason is, one of the basic reasons the biofuels are not that efficient is that if what I'm showing you is the solar spectrum, right? And as you can see, the absorptions of the chlorophyll, which is responsible for the photosynthetic process, it does not absorb anything in the infrared, whereas almost 50% of solar radiation is in the infrared. And so it only absorbs the radiation in the visible range, and even in the visible range there is a minima, which is around the green, because the plants are green. Whereas if you convert the solar spectrum into heat, that means you can tap into all the energy in the solar spectrum and then use that energy to store or make a fuel. So the process could be that you have photons and you convert them into phonons, and then phonons can just go and storing that energy in chemical bonds. So that is what led to the third part of the HEATS program, where we were looking at storing solar energy into in form of fuel, but not using biofuel route or the photosynthetic route, but the thermal route. But there are challenges. If you do, for example, direct thermolysis of water, direct thermolysis of water will take place at 4,000 degrees Celsius. So that is a non-starter. So the question is, what are the other ways? So there is, people have been looking at this kind of a metal oxide redox cycle, where you can significantly lower the temperature from, say, 4,000 degrees Celsius to people have shown around 2,000 degrees Celsius or so. We put a forward target of 1,500 degrees Celsius as your high temperature site. And the way the cycle works is that you have metal oxide, you take it to a higher temperature, and then by heating it through the solar radiation, and then oxygen comes out, and on the other side you cool it down, and then you react it with steam or carbon dioxide, and you get a syngas, right? There is significant potential of heat recycling and harvesting in the system, but in whatever result is available in literature, people were not doing it. And that actually, you really need that part of in the technology to make the efficiency greater than 10%. So that is one example. So we have funded a couple of projects looking into this kind of a system. And we actually also found out, this proposal that came in. It was initially we were not expecting something like this, but this is a proposal that came from MIT, where they were looking at storing the solar heat in sort of a fuel, where the idea is that the stored energy is stored based on changing the molecular shape. So what I'm showing you there is a molecule. As you can see, there's a change in the shape when it absorbs solar radiation, and in the return, with some kind of a trigger, you can get that energy in form of heat. And this system can be in a liquid state. It's like a solution, and then so it's like a gasoline. And once you have used that energy, you can recharge it back. People have looked into this kind of a system for the last 25 years. The challenge was that the energy density was 4 orders of magnitude lower than lithium-ion battery. Very, very low energy density. What this team has figured out is how to significantly boost. The target is approximately 4 orders of magnitude compared to what is available in the literature for the energy density. So this is another one of those ideas that we funded in the thermofuels part of the program. Okay. So I think this is the most interesting part, is where I think we should brainstorm together. That what else? These are some of the programs that we have funded at ARPA-E, but we have internally thought about it, but we don't have a program, and we would love to hear from you that which one of these, or maybe more, other ideas that ARPA-E should be looking into, and is there a significant white space which has not been tapped by any government agency or the private sector, and we should put money behind it to significantly improve technology related to thermal energy systems. So these are some of the ideas. One is switchable insulation. Can you have an insulation which can conduct or insulating? But there are some data in the literature, but can you have a very high contrast switching? The data in the literature that you'll see is typically 1:2 conductance is 2 times that in the insulating state. Can you have 10:1 or 100:1? Long distance heat transport. Can we have, just like long distance electrical transport, can we do long distance heat transport? Personal thermal management. Can we actually have fabrics, for example, which can automatically switch on and off depending on what the temperature is? Actually, I just came to know from Karma on her carbon capture work that all solid state heat exchangers. So you have solid particles flowing through a pipe, and how does that transfer heat with a heat exchanger? And some of the other obvious ones is high efficiency engines. We haven't done anything on that. Very high temperature materials, and combined heat and power systems. But we haven't really done much, and we would love to hear from you guys that what you think of some of these ideas and even some more ideas. With that, I think I'm just going to end, and we'll be happy to take some questions.
Ravi, can I chirp in for just a second? I just want to chirp in for a second. We threw up this list partially to just sort of get people's, juices flowing, but also I think it helps to give some insight into, what programs we've done and haven't done. And there are various reasons why we haven't done programs in these areas, right? One might be, and I'll just take an example, right? You might think of personal thermal management. Interesting idea. What if we didn't have to air condition our rooms? We could just air condition the bodies inside them, right? Why haven't we done it? Well, one question is, would it actually happen, right? Would people actually, if you did develop the technology, would it ever be adopted? Would people be willing? What happens to their faces, right? I mean, these are questions of would it actually turn into an impact? Switchable insulation. You'd think of, well, is there actually a reasonable approach out there, right? Or is this just a figment of our imagination if we wanted 1,000-to-1 switching at extremely low costs, right? Same thing maybe with long-distance heat transport. Would it happen? Are there good ideas out there? But the other thing to realize is that some of these areas, we just haven't done a program because we haven't had the bandwidth or the people yet to do it. And so if we're really interested in hearing from everyone here, what are areas that fit the ARPA-E model, right? High impact, innovative ideas, and there are enough out there that we could actually fund a portfolio of approaches to go after them that are all high quality and have high teams. But, if someone's passionate about one of these spaces, we need folks to come work on these areas as well at ARPA-E. So just wanted to throw that out before we begin the discussion.
Okay. So why don't we take some questions in the remaining,
So there is a microphone at the center of the room. You can go there. And
I think
walk with that.
There's a question right there.
And then, yeah.
So folks can line up. We also have a mic that we can pass around.
Should I step out?
No, you're fine.
You can go right ahead.
If it works.
Carl Wyatt, Creaser Research Incorporated. In looking at the notion of being able to do energy harvesting, particularly heat, do you have any interest in the potential for solid-state devices, which can essentially collect ambient heat with high efficiency and then convert that heat to electricity, which then could be stored in capacitors? Obviously, I'm asking the question because I think I may have a solution. But the notion of being able to develop a new class of solid-state devices, which, when properly doped, actually exhibit the following property. If you take these devices, they're made with conventional semiconductor manufacturing techniques. You let them sit on a table at room temperature and then connect a capacitor. And what you discover is that the capacitor actually charges. There is a pulse of current that flows, and that the energy density associated with that charging event is 200 times what you see in chemical battery systems. This, we think, opens up a potential opportunity in that it not only allows for the potential for efficient energy harvesting from ambient heat, anything from your exhaust pipes in your automobiles, to room temperature and other applications. It appears to be a scalable phenomena. That is to say, you can get power out of the device that spans several orders of magnitude. And the notion that you create electrical energy lends itself to convenient supercapacitor type storage for subsequent reuse. So then if there is that type of a thermal system, which essentially is harvesting ambient thermal, would that be of interest?
So first of all, I think let me take a broader outlook on solid-state converters. So we have funded a couple of programs on solid-state converters, heat to electricity, on thermoelectrics. But we haven't, as I mentioned in the beginning, that we haven't really had a focused program on either ambient heat that you're talking about or waste heat to convert it. But ARPA-E definitely has a lot of interest in those kind of technologies.
I'll just mention before we kick into the discussion, ARPA-E does have a draft FOA on the street for an open solicitation. We're trying to get input. It's just sort of a disclaimer that we have that we're going to have a discussion about some of these ideas. And folks should know that if there does end up being a FOA that relates to any of these ideas, right, what we're saying here has no bearing on selection process of anything for any FOAs, right? Anything that's a response or a proposal to a FOA will go through that formal process. So that's just kind of a formal disclaimer before we get into this. There are going to be a lot of questions of are you interested in this and that, and so these are kind of two separate things.
I would, however, just add one thing to that if you are in the situation this gentleman's in up front. Oh, I'm sorry. Yeah, if you are in the situation that you're in up front, I do encourage you to read the draft FOA that's out there. I think you'll learn a lot about the type of things that that we're looking for and the way we think about energy technologies from reading that document. It's a draft funding announcement opportunity that's on the ARPA-E website.
Yeah, and generally speaking, I think reading about the existing programs that we have and all of the archive funding opportunity announcement, the solicitations that we've put out, are still up on our website and accessible. So you are able to read up and see how we crafted the programs we've already put out and funded, and that'll help give some perspective in terms of how the agency's thinking. Next question.
Yes. Sawyer from CGI Technology. Mechanical pump can consist of a simple solar panel with couple of fans and can convectionally recirculate energy that are existing within any structure. In attic, we have tremendous heat energy. In crawl space, we have tremendously cold energy. You can change the time of the day to the night and night to the day and take advantage of these energies. This has been overlooked for so long because of accessibility and cheapness of energy such as fuel, fossil fuel, and electricity. Another thing is, very simply, thermal capacitance can consist of water. Water is the best heat storage, has the best heat storage capability, and can be used. In a study by NASA, a simple 3x5 window can generate over $300 a year on average heat energy. Why this heat cannot be stored in the water? I have a patent that I put water in a window and take advantage of thermal capacitance of that. These are simple matter. I don't know why we need such a complex material to go to that extent of expense to create a thermal storage. I am inviting all of you to look at my patents in this simple matter, and let's not overlook simplicity. That would drive the, if we stay in the same direction, we're going to have by EPA and Department of Energy guideline of having E-windows. E-windows are wrong concept.
Yeah.
We are reflecting 70% of radiant heat to any window.
I think we understand the position you're going with, just so that because we're running out of time, we should probably answer the question. I think that you've got a very good point. I mean, there's a lot of value to using very simple and inexpensive materials to achieve the same goals. Certainly we would not want to go for some sort of, rhodium storage material to use for, a concentrated solar power plant that's not cost effective. Your point is well taken.
Can I ask?
I would just add, I would like to just add that we looked at water, and then we had the applications that we have in mind. That's when we realized that water is not the right storage material for those applications. But you're right, in certain applications, water just makes sense.
And I think this is a question about what ARPA-E is about. So this is the important piece of this, which is just because ARPA-E isn't sometimes interested in the simple solutions, right? It's because that's not our mission, right? Our mission is to go for very high impacts with really kind of transformational, new, innovative approaches, which generally aren't that simple. And so that doesn't mean that simple approaches aren't important. It doesn't mean they can be a big impact. It just may not be something that's a right fit for ARPA-E sometimes. But it's always on a case-by-case basis. So I think we should take the next question, and we can follow up afterwards.
Thank you. My name is Mike Hart. I'm the president of Sierra Energy. We've got a waste gasification technology, and we've been demonstrating it with the Department of Defense back at the Renewable Energy Testing Center. And I've got a white space for you. Our technology can take any form of waste. We've demonstrated it. Garbage, any sort of biomass, medical waste, etc. We gasify it, and we recover all the metals. We recover all the liquid solids. The issue then becomes we create a syngas, medium BTU. It's about 400 to 500 BTU per standard cubic foot. The issue is it's coming out at about 1,200 degrees centigrade. And so you've got a mix that's 70% carbon monoxide, 30% hydrogen. Conventional technology tells us we need to now take that gas and we need to cool it to run it through a typical reciprocating engine or something at the scale where we're operating. We're commercializing this right now at 25 tons a day of waste. We're working with a lot of small communities where this is a perfect solution for them. There's a huge amount of wasted energy in doing that. And the question is there some sort of technological approach where we could take this hot syngas, coming out and more directly converted into some form of energy without wasting that cycle of cooling the syngas, wasting it essentially, so you can then run it through conventional compressors and then either take it to FT diesel or taking it to conventional electricity. If we were to take this, like we can run it 25 tons per day, we can make 1.25 megawatts consistent electricity using a CAT reciprocating genset. We could double that with combined cycle, but the problem is they don't make it at that size. And I apologize for going on so long, but we're looking right now, we could put thousands of these systems in the United States right now, just based on the communities that are already approaching us and DoD installations we're talking to. The problem is, what do you do with hot syngas? So, thank you.
Well, one thing I'd just quickly chime in is when it comes to waste heat conversion, and Ravi can chime in and Karma, I think one of the things we've struggled with is when you look at waste heat sources, they're sort of all over the map, right? Different scales, different temperatures, different qualities of heat. And so there's the question of what would an ARPA-E program look like that captures all of that into one coherent set of targets, coherent set of metrics. And for instance, your smaller combined cycle plant, well, what's the right size and what's the right temperature to really maximize the impact? It'd be good to get folks' input on that.
What you raise is a very important question. We are internally doing research right now, looking at the whole spectrum of different sources of waste heat, at what temperature the waste heat is coming at, and doing analysis to figure out if there is a technology out there. Let's say if I give this technology, if we have this technology. So from ARPA-E point of view, we're looking at, okay, if there is a technology with this kind of different efficiencies, what will be the overall impact? So that analysis is still going on. And we haven't really decided, once the analysis is complete, that whether we are going to have a program on that or we will not have a program on that. But US is very, very important. This application I was not aware of, so thank you for bringing it up to our attention. I was not aware of this application.
So it looks like our time has expired for this session. I will reiterate what Eric Toon said in the first session, that we do have an open RFI entirely because we want to be able to receive impact from all of you. We have a lot of value to taking that snapshot.
We can take probably a couple of questions. Right?
Do we have time
Can we take a couple of questions?
No, we're done, Dave.
I'm sorry? The deadline for the open RFI.
So the open RFI will be, I believe it will remain open for the.
It's on the website
now,
and we can get that to you. Sorry that we don't have that on the top of our heads.
I believe it's around the end of this week is about when it closes, but don't hold me to that. But that's the time. That's the rough timeline. Wednesday.
But I just want to. Unfortunately, we are running out of time, but I'm around. All of us are around. Just feel free to just talk to us, stop us in the hallway, and discuss things.
Thank you all.
Thank you.